Okay, this problem, we have an Atwood machine. We have two masses, m and 2m, are the same height, h. This pulley has a mass little m and radius r. And then we set the system in motion. So that's going to accelerate down, m is going to accelerate up. And we're supposed to answer these questions. So some assumptions we're making is that the cord, this cord right here that wraps around is long enough, is much longer than h, so that when 2m hits, and basically 2m goes down a distance h, m goes up a distance h, it's way shy of the pulley, okay? So what's the acceleration of the system when we let go of these masses? How many revolutions does the pulley make? And when this one falls a distance h, and how high above the ground does this go, after this big one hits here. It's already at a height h, right? So this one's going to go down h. It's going to go up h. So that's already 2h up the ground. And then when this one hits, this is going to continue going up for a little bit in free fall until it basically reaches a maximum height, right? So we need to find how high above the ground this mass goes, the maximum height. All right, let's begin. So that's the problem. So let's draw a free body diagram. So for A, do a free body diagram for each mass and the pulley. Okay. So for mass M, you've got the weight down, mg, and the tension, I'm going to call it F1 or T1, right? Because the pulley has mass and radius, and we're going to take that into account. The tension on each side of the pulley is not the same. Okay? So that's for mass M. For mass 2M, we have 2m times g pointing down, tension 2 pointing up. And for the pulley, it says mass m and radius r. Here we have T1. Here we have T2. Now, obviously, the system is going to move clockwise. So like this. So that's the positive. And for both of these, not for both, for this one right here, positive is down. For this one, we're going to take positive is up. We always take positive in the direction of the acceleration. So little mass, or just mass m, is going to accelerate upward. So we take plus up. The mass 2m is going to accelerate down. So we take the plus to be down. And the pulley is going to rotate clockwise. So we take clockwise to be positive. All right, for the torque. So now we write Newton's equations for each mass, okay? So for mass m, right here, so for m, we only have one dimension. So sum of all the forces is ma. By the way, the masses have the same acceleration, right? So how many forces do we have acting? We have T1 in the positive direction, mg in the negative direction, that's why it's a minus, equals ma. Okay? So this is equation 1. For mass 2m, we have 2m times g pointing down, so that's the positive, minus T2 equals the mass times the acceleration, and the mass is 2m. Okay, so that's equation 2. Now, for the pulley, we have a net torque on the pulley because the tensions are not the same. So for the little mass m, the pulley, okay, we have a net torque, and again, positive is clockwise, and what's causing the clockwise torque is T2. T1 is trying to cause counterclockwise torque. Obviously, T2 went over T1. So T2 times R, then let's just put it, sum of the torques is I alpha. I is the moment of inertia of the pulley. We have clockwise torque minus counterclockwise torque is I. Alpha is A over R. Okay, is the acceleration, the tangential acceleration over R. Now, what's clockwise torque? Again, it's T2 times R minus T1 for the counterclockwise times R. I is 1/2 little m R squared times A over R. Okay, so T2 minus T1 divided by R, both sides. 1/2 little m, let's go up here. Little m is capital M over 4. So capital M over 4 times R squared, A over R squared. Okay, because I divided by R both sides. So this cancels out. 1/2 M over 4 gives me 1/8. So T2 minus T1 equals 1/8 MA. This is equation 3. So we have 1, 2, and 3. So remember, I don't care about T1 and T2. All I need to do here is just simple math. Add up equation 1 plus equation 2 plus equation 3. We add the left side with the left side and the right side with the right side. So I have T1 minus mg plus 2mg minus T2. So this is equation 1. This is equation 2. And equation 3, I have T2 minus T1 equals, so this is 3, the right side of 3, the left side of 3. Now the right sides are MA for equation 1 plus 2MA for equation 2 plus 1/8 MA for equation 3. As you can see, T1 and T2 cancel out, and 2mg minus mg, I get mg equals MA plus 2MA is 3MA plus 1/8, give me, let's just do it slowly, 3MA plus 1/8 MA. M cancels out. I got G equals 3 plus 1/8, that's 25/8A. So A equals 8 over 25G, which is good. First, because it's less than G. Okay, if we got 25 over 8G, that would not have been good, right? 8 over 25G. All right, now we got the acceleration. Part B, does part B say, how many revolutions did the pulley make when the mass started moving till 2m hits the ground? Well, there are two ways of doing this. We can compute the time it takes it to hit the ground and all of that, but we could do an easy way because we know this mass fell down a distance h. That means which caused this one to rotate a certain angle. So that's a very easy one. So we know that theta, or basically, theta equals first, the height equals theta times r, right? Okay. Because that's how much the rope got unraveled, which is h. It caused this many radians to be the pulley to rotate this many radians, and the radius times the radius of the pulley. So theta equals h over r, but this is in radians. So to change it, this is in radians. So to change it to revolutions, will be h over 2 pi r revolutions. That is theta. Okay. Again, we could have done it another way. Could have said theta is theta 0 plus omega 0 t plus 1/2 alpha t squared. Obviously, this is 0. This is 0. So theta is 1/2 alpha t squared. Remember what alpha is? Alpha is a over r. So we need to get t in this case. So let's get t. So we could use y. It's y0 plus v0 yt plus 1/2 at squared. Actually, we need to get t squared, right? So if we look at the drop, here's 2m, fell down a distance h. So here's my axis. Okay, I want to choose it. Yeah, that's fine. I want to choose my axis maybe down like this. Okay. Let's put it up here. Here's the 0. So I start from 0 and I go a distance y down in the positive direction. So h is, I start from 0. Initial velocity is 0 plus 1/2 a was what? Right there, 8 over 25 g. I'll keep it as a for now. At squared. So now get for t squared. So t squared is 2h over a. So let's take this t squared and stick it in here to get theta. Theta equals 1/2 times alpha. Alpha is a over r times t squared, which is 2h over a. Okay. So a cancels, 2 cancels, we get h over r, which is right here. But again, remember, this is in radians. So which is equal h over 2 pi r revolutions. So this is in radians. Okay. Same approach, okay? But we needed to get time in this case, which we may need to use for the other case, for part C. So this is how many revolutions does the pulley make, or the pulley makes during the fall of 2m, okay? So part C, how high above the ground does m rise after 2m hits the ground, okay? All right, there's no tension after 2m hits the ground. So what's happening to m? Let's draw a little diagram to see what's happening to m. So here's m's initial position. Nothing was moving. It was at a height h above the ground. Then things get into motion, and right before 2m, which is right here, hits the ground, this one also goes up another height h. Okay. Now that 2m hits the ground, this is free of any tension or anything like that. The only force that's acting on it is gravity. So basically, this is in free fall right now. So that's going to go up, and before it comes down, it's going to stop. It's going to go up a distance d. Okay. So let's focus on, first of all, we need the initial velocity here. It's going at some initial velocity. Here, at some final velocity is 0 because it reached the maximum height. And we can relate these two with respect to d, because we have this equation, v squared or v final squared is v0 squared plus 2a times d. And a here is negative g because, right, the acceleration here is gravity. Here the acceleration is gravity. Here the acceleration is a. Up, here, g down. Okay. So once we get to the final stage, we're good to go. The only thing we need is v0, because we want to see right before when 2m hits, how fast was m going up. Okay. And again, that's easy to figure out, because the speed of m at this point and the speed of 2m right before it hits the ground are the same, right? So we can easily compute the speed of 2m as it goes down. And what is that? Let's look at it separately in a separate diagram. Here's 2m. It has to go down a distance h, hit the ground. So here it's got some velocity. Here, velocity v0 is 0 because it was stationary. Then we let go. This block goes down under the acceleration a, and then hits the ground. So right before it hits the ground, it's got this much velocity. This will serve as the initial velocity for m at this point, right? Because m and v have the same velocity as long as they're connected still. So right before 2m hits the ground, m has its same velocity as 2m. So here we can easily compute this, right? Again, take our axis like this. Here's 0, so we can write y. No, actually, we need the velocity. So v squared is v0 squared plus 2a times the height, which is h. This is 0 because it was let go. So v is the square root of 2ah, square root of 2 times a. A was 8 over 25g times h. Okay. So 2 times 8 is 16 over 25. Both of those come out of the square root as 4/5 gh. So this is the velocity. So this is velocity of 2m right before it hits the ground, which is the velocity of m. Okay. So again, in your mind, as this one goes down, distance h, this has to go up a distance h. And right when that h is reached, this is moving up at some velocity. I'm going to call it v0. It's the same velocity that this one is about to hit the ground with. So now we look at the latter part, the free fall part of mass m, which is this one right here. So now we have mass m, which is already 2h above the ground, going up some velocity v0, some distance d before it stops at the maximum height. And then, of course, going to come down. But we're not interested in the downward motion. So how do we set this problem up? Again, we've got initial velocity, we've got a distance d, and we've got an acceleration down. All we want to find is d. Okay, so we can look at this as the velocity final is here's our axis. So here's the 0, up is positive. So v at the top squared is v initial squared plus 2a times d. Well, what's the acceleration a? Now we are in free fall in this step. So the acceleration is negative g. Why is it negative g? Because g is pointing down and my positive sense is up. So v final squared is 0. v0 squared, which is, by the way, this one right here. Let's go ahead and plug it in, which is going to be 16 over 25 gh minus 2 gd. So g cancels out, obviously. So let's move things over. So we're going to have d equals 8 over 25h. That's how high above when basically 2m hits the ground. That's how high this keeps going. So height above ground, h, is its initial height plus the height when it was moving with 2m, right? This went down a height h, this goes up a height h, plus the free fall height. So this is 2h, and here's an h, so that will give me 58 over 25h. That is how high above the ground mass m will go. Okay, and that's the problem. Thanks for watching.